All right, let me try a good conceptual one. It's number 31, and it's one that emphasizes the large amount of latent heat of ice. And in fact, the video solution I just did for number 22, I was talking about that. So if you want, look over at the video solution for number 22, because I went through and showed what an enormous amount of energy it took to melt the ice. And that's kind of what this one is getting at. Let's read it here. It says 100 grams of ice at 0 degrees. All right, so here is 100 grams of ice. It is at 0 degrees. And so it's getting ready to melt, okay? So it's not like it's just coming out of the freezer. It's not like it's really cold. You've already taken it out of the freezer and it's been sitting on the table, so it warmed up. And now the edges is starting to melt. So it's warmed up to 0 degrees, okay? So 100 grams of ice at 0 degrees. Now it is added to, and I'll just put it adjacent like this. Obviously, it would kind of mix together, but you would have 100 grams of water at 80 degrees Celsius. Okay? And it says, will the equilibrium temperature of this mixture be greater than or equal to or less than 40 degrees? Now, here's why they picked 40 degrees. They picked 40 degrees because if you accidentally or carelessly forget that it takes a lot of energy to melt ice, you might treat this as if this was just water at 0 degrees. And of course, since you have exactly the same amount and exactly the same material, when you mix them, you would expect them to meet in the middle. This would cool down the same rate that this one would warm up, and you would expect, in that case, 40 degrees Celsius. Now, that is wrong, but that's what you would get if you forgot that it took a lot amount of energy to melt the ice. So they gave us an easy way. We could easily just answer it is definitely less than 40 degrees. Because the first amount, when this starts cooling down, let's just say it cools from 80 down to, I'll say 60. And I'm just making up a number for a second. But if it cools down to 60 and then it melts all this, that's where the energy goes. Now you have water at 0 degrees. So then I would say you have 0 and 60 and it's going to meet at 30, okay? Or maybe it would take even more. Maybe instead of it cools down to 60, maybe it cools all the way down to 40 before it melts all this ice. Okay. But once you do that, you then have water at 0 degrees, and then of course this is already cooled to 40, so they'd meet in the middle at 20. Okay, so no matter how you cut it, as long as you remember that there is energy needed to break these bonds, there is a latent heat here, you're going to say it's less than 40. And that's enough to answer the question. But I'll take it even one step further here and go, okay, what would this final temperature be? And I would say, okay, let's do a little bit of arithmetic here. Let's just ask this question, how much energy would it take to melt this ice? And that's this MLF. So we've got 100 grams, and the amount of energy it takes, we can look this up in table 2, the latent heat of water, is 80 calories per gram. So when you multiply that together, it's going to take 8,000 calories in order to melt all that. So now we can come back over here and say, okay, for this ice to get the 8,000, it must have come from this water. So this water must have gone down. Remember earlier in my discussion, I said, well, maybe it goes down to 60 or maybe it goes down to 40. But now I have a number. I could actually tell you what it would go down to. And I would just say again, what if it goes down to 40 before it melts all this? If it goes down to 40 before it melts all this, then this would melt and this is down to 40 and it would meet at 20. And that's how I would get the final temperature. So let's see. So now I'm going to do a calculation, MC delta T. This would be the cooling down of this warmer water. And again, we have 100 grams, and because it's water, it's 1 calorie per gram per each degree. And my question is, what would the change of temperature be? How much does this have to go down in order to release the 8,000 calories that is needed in order to melt all this ice before we can decide where they meet in the middle? All right, well, let's do this change in temperature. And so calories would cancel off, grams would cancel off, and as far as units go, you would have degrees Celsius. And then if you divide by 100, you get 80. So this thing has to cool down 80 degrees to give off enough energy, which is 8,000 calories, in order to melt all that. All right, so it's already at 80. So if it cools down, it's going to go all the way down to 0 degrees. And what's going to happen, it's going to melt all the ice, so you're going to get ice at 0 degrees. And they're going to meet in the middle, which is 0. And so the final temperature would be 0 degrees Celsius if they were asking for, what is the final temperature. And so it's an amazing how much energy it took to melt this ice. You had to take really warm water. This is 80 degrees. This is really hot coffee. And you have to cool it all the way down to 0 degrees before you're going to melt all that ice. And so if you had a cup of hot coffee and an equal amount of ice and put them together, they are going to reach 0 degrees. Not all the ice will melt, but they're going to be at 0 degrees. All right, hope that one helped.